Is it ringing?
It's ringing, but he's not picking up. I'm gonna try another number.
Do you know his office number? He's apparently in his office.
Yes, just give me a second. I'll figure this.
He's back. He's back.
Is he?
Hi,
Giulio?
sorry. Yes, I am now. I got stuck with, I think internet broke it down and then.
We also realized we forgot to press recording, so we are recording halfway through. Hopefully it's okay.
Oh, so yeah, but also anyway, can you hear me now? Sorry.
Yes, yes.
It's okay, I'm sorry. Any questions so far? Let me give you the application about the moduli space now. So we have, let me put M n of V, the moduli space of case B variety. So the case B moduli space, which is projective, as you know. So dimension equal to n and volume equal to V. I'm not including pairs because for some of the results, for many results, I cannot work with pairs. First, because if you have pairs that is delta reduced and the normal issue, the normalization, there are many issues. So I'm not, it's just a moduli space of varieties, not of case B pairs. So I take the moduli space of case B pairs, so case B variety, and I do as before. I have the universal family here, and I define the lambda CM line bundle as taking the cycle relative canonical bundle to the power n plus 1 and push it down. And I take lambda m, the mth Chow class, which are the determinant of the push forward of the sheaf m times kv, k pi. Okay, so this K is ample. This one is ample. This is known by Patak-Falvey and Shu. This other one is Neff, just Neff. This is by Fujino. Okay. So the theorem we have now is that what is the theorem? So take Q and M as integer as before, such that I don't know. Let me say that MQKF is a Cartier for every F in the moduli space. And then the result we have is that lambda Cm minus epsilon of lambda m is ample on the moduli space M and V for every epsilon in the interval from 0 to 1 over, what's that? Q to the n, m to the n plus 1, open here. Okay. So we have also variant about this. I will show you some variants in a second, but so let's look at it. It says that what does it say? It gives you a portion of the ample cone. So lambda Cm, you want to think at it as a line bundle inside the ample cone, so in the interior. Lambda Cm might be on the border of the ample cone, on the boundary, and it says how much you can subtract of lambda m to the same line bundle to remain in the ample cone. So gives you a small segment which starts off from the CM line bundle and moves out of the ample cone, and it tells you that you stay in the ample cone for a little while. So it's a quantitative result and tells you how big, not how big, how big at least is the ample cone. So it gives you a portion of the interior of the ample cone, which of course depend on the geometry of the variety parameterized, of the parameterized variety. So I'll give you variant about this result. In here, for instance, we have this case table, which is not what we're looking at. So something like, so this was this result I was telling you. Okay. And we have another result where epsilon range in a different interval, where here you say very little w here, which is the volume. So if you can study the volume over varieties in your moduli space, you get another boundary which speaks about the volume of the variety parameterized in your moduli space. This speaks about Cartier index of numerically finite maps. And according to these quantitative things, you get a portion of the ample cone. So the question are, of course, okay, maybe how sharp are these results? Before telling you what the precise question, I will define, maybe we introduce this notion, which is not very crucial, but somehow it's fun. So the neurons, the lambda Néron-Severi group of your moduli space is the span of lambda CM and the lambda M for every M. So this guy is a subspace of the actual Néron-Severi group. And then the lambda Nef cone is just the Nef cone of your moduli space intersected with this lambda Néron-Severi group. Okay. The question are two. Question one, is the dimension of this lambda Néron-Severi group equal to n+1? And question two, do our results describe the full lambda Nef cone? Okay, so both are true for curve when n is equal to 1. In general, here for the first question, we can prove something under some condition. And here, this we don't know anything, not even about surfaces. So our result describe a subcone of the Nef of this lambda cone. I don't know, we don't know if this is everything or not. Okay. How much time do I have left?
You have 30 minutes, Giulio.
Oh, okay, I'm halfway, cool. Any questions so far? That's what the main statement. I want to give you some idea of the proof now. But do you have questions about the statements? Or anything you want to say? I'll drink some water in the meantime. And also change the paper. So the plan now is tell you something about the proof of these results. And then if I have time and you like, I can also tell you something about the Fano side of the story, because that's just the case table. Okay, so let me go to the idea of the proof. So as I told you before, we have many different slope inequalities, many variants. So I will not prove properly any one of them. I will just give you an idea about how to approach this problem. Actually, I will prove one slope inequality, the easiest one, which is not very meaningful, I will tell you, but let me give how to approach this problem. Let me explain this. So we introduce, okay. So we go this way. So first we define E to be the push forward of OX, maybe M time, doesn't really matter. Let me put M time next. Okay, this push forward. Maybe I will put M big enough so that this is Cartier, just to make things easier. But also we can put M equal 1 or the bundles here. Let me do this one. Now we look at the HN. We have the HN filtration of E. So maybe I want to use more screen, so we'll put this maybe, you know, here maybe. So that's better. So you can see it. This is a vector bundle on T. So we do slope stability for this vector bundle. So we have the Erdner-Riemann filtration of E, which will be denoted by EI. And then I have the slopes, mu I, which is EI plus 1 divided by EI. Or maybe I don't never know them. Maybe sorry, I always, no, I will not do this way. I'll just maybe do EI divided by EI minus 1. So you have the first slope, which is the biggest one. Then you go strictly maybe to mu2. And then that's the slope of this guy. And this goes down up to mu L. Okay. Now the key fact is a result of Fujino. Tells you that E is NEF. Okay, which is equivalent to say that the last slope is at least 0. The reason is as F is case-B stable. So that's the first step. So case-B stability implies through a result of Fujino, which is very deep, a positivity result, which is this vector bundle is an F vector bundle, which concretely means that the slopes are all non-negative. And here you need to apply Fujino, you need either this delta to be reduced or this guy to be Cartier. There are some issues here. So you need M big enough. I mean, there are some technical issues, but apart from this, you need that this result tells you that the stability implies the positivity, the non-negativity of the slopes. And let me also say that this was the stability result used also by Xiao. Of course, Xiao didn't know this very general theorem, but for a family of smooth curve, this Fujino result was well known before. So it essentially used this stability. Because of this, I told at the beginning Fujino was using, sorry, Xiao was using case-B stability. Not quite, of course, it's general notion, but he was using that in that setup, this vector bundle is NEF. And this is what we are using too. So, okay, the other, okay, so that's the big result. The triviality, I can say that also E, if you tensor it by O of T minus mu L of a point P, say, is NEF. Just because being NEF for a vector bundle means that all the slopes are non-negative. So if you twist back by the slopes, still you're NEF. That's exactly the NEFness threshold. So in particular, what you get is that if you take Kx over T plus delta, I mean, M times this doesn't matter. So maybe just to simplify things, let me call M of X over T plus delta equal to L, just to simplify the notations so that I can use L. This means that if you take L minus mu L of F is NEF. I.e. what I'm really saying is that mu F, if you like, mu L is the NEFness threshold. NEFness threshold. Sorry for my bad writing, but concretely, L is concretely, Fujino tells you that L is nef, E is nef, L is nef, but it's not only nef, you can take away from it mu L times of the fiber, still it remains nef. So in particular, L minus mu L of f to the power n plus 1 is bigger or equal than 0, which in particular means that L to the power n plus 1 is greater or equal than, I think, n plus 1, the volume of a fiber, times mu L. Maybe I can take m equal to 1, I don't know, doesn't matter, just to simplify things, times mu L. Just I'm developing the power here. This is the volume with respect to the canonical bundle. So that's all trivial, but now we cannot go much more than this unless we take more positivity. So we take more positivity, more stability, which is more or less the same thing. So we assume that this E is semi-stable, semi-stable. So if this is not a natural assumption, this will not be true in most cases. I'm just making this assumption to give you a simple proof of a slope inequalities. So under this assumption, L is equal to 1 because the Arden-Erasmus filtration has length 1 as E itself is already stable, semi-stable. So mu L is the slope of E, which is nothing but what? The degree of this guy, the degree of E, if you like, divided by the rank of E. So the upshot, so the inequality we get is that if you like, let me kxt to the power n plus 1. Maybe let me also put delta equal to 0, so I give you an easier statement, is at least n plus 1 times the volume of a fiber divided by the H0 of a fiber with the canonical bundle times the degree of this push forward. Okay. So that's a slope inequality we can prove this way. So we are in this setup. This is not very realistic. I made many assumptions. I skipped some technical details, but doesn't really matter. The very strange assumption I have made is that E is semi-stable. So the Arden-Erasmus filtration has length 1. So this won't be true in general. Okay, because I mean the point is that if you are semi-stable, then then you know this thing is at least 0, but they won't be true in general. This I want to say. So we cannot go this way. We have to start back from here. Okay. So we use less positivity. So what we do is the following. We do the following construction. So we have this EE inside E. Okay. So we take BI to be the relative base locus of EI, i.e. what you have for every T in T, the restriction of E at the point T sits inside the H0 of the fiber XT LT. Okay, so you take B E at T is the base locus of EI at T. Now you make all base loci divisorial. Okay, so you blow up X. I will not change notations, but I will replace X from some big blow up so that X becomes smooth. Why not? But what is more important, that all BI becomes divisors. So we are in characteristic 0, so we can do it. And now in this new model, we define mi to be the L minus Zi. So Zi is the divisorial base locus. So it's the base locus. Let me put it this way. Okay, I change the notation from Bi to Zi because now the base locus is a divisorial. And I also, so this Mi is F globally generated. Just because I have removed the base locus. And now I define Ni as Mi minus the slope mu I times a fiber F. And now the key lemma is that Ni is Nef. Maybe I will prove you the lemma, which is kind of easy. Proof of the lemma. You have this, that the idea of the proof of the lemma, but I think is instructive, is that if you have the EI tensor and you take out of it minus mu I of a point, P is Nef. Just because mu I is the stability threshold of this bundle. Because the slope of this bundle are non-negative, but the lowest slope is mu I. So if you take out mu I, still they're all non-negative. So this is Nef. And then you have an evaluation map from F upper star of this guy, tensor OT of minus mu I P, to Ni, which is surjective here as Mi is F globally generated. So Ni is Nef. So I have given to you at least a complete proof. Question? No, that's okay. So now you let Pi to be Mi restricted to a fiber F, which is equal to Ni restricted to a fiber F. And now we have a proposition. I mean, I will show you it on the paper, the more general things. But you have something like this. You have that if you do NL, so the last piece to the power n plus 1, this is at least sum from I that goes from 1 to L of something like Pi plus 1 PL to the n plus 1, no, n minus 1, sorry, let's beg your pardon. Minus 1 times the numbers mu I minus mu I plus 1. Okay. So you have such an equality. What is this? This, if you look at it on this side, you have more or less L to the n plus 1. So this was the guy we want to lower bound. So that's good. Here you have an intersection number on F. So that's something we leave just on the general fiber. So this will read off some geometry of F. And they had the difference of the slopes here. So I will not prove you this result for you, but you use in a crucial way that Ni is Nef, and you work with Ni. You have to put all the Ni together and work a bit, and you use the term Nef. That's very important. And you get this result. So here you are happy. Here, you will study these intersection numbers on F, and here you have these jump things. Okay. And actually, maybe I will show you the paper. Just for the sake of completeness, what we really do is more general things than this. That's not to section 3. You have to go to section 3. I will get back to section 2 later, and I will tell you why we have this order, which is kind of reverse. Sorry, I think it's. You see, we have lemma of this form. You have many intersection numbers. It's quite complicated. With many, you have more complicated results. Especially this color, this is what you're going to use later. I mean, we have more complicated intersection. Very many, we have many different equations on the form. So that was the easiest one that I wanted to share with you. So here we are happy. Here we have to work. Now to work with this, we have a very easy lemma. So this lemma is very easy to prove. The second one is that the degree. So this degree, which is what we want to have here, we want that this is bigger than something times this. But this one is equal to the sum for either towards the 1 to L of the rank of EI times mu I minus mu I plus 1. So the connection from here to here pass through this formula. Now, but we have this here. Now the rank of EI is at most the H0 over the generic fiber of PI. That's the construction. So this things goes here. This things has to go to this rank of EI things. And to go the way, you need some other custom norm inequality. That's a chapter 2 of our paper. The section 2, sorry. Okay, so that's a problem on F. So this is all on F. So now we look at the generic fiber F. We have these intersection numbers computed on F, and we want to go back to this section, this H0 here. And for instance, let me speak about another inequality. The classical one tells you this. If you have S as smooth, minimal surface, then K of S squared is at least 2 times the H0 of S, K of S, minus 4. So you see, you have an intersection number which bounds some H0. So that's what we want to do. We have intersection numbers and we want to bound this, which then will bound this. To put everything together and get the slope inequalities. So we have many divergent generalization of this result. So let me tell you just one result. So another theorem. So you get F, the last theorem, F normal projective variety. So this will be applied to one fiber of F, of little f. So one fiber of the family. So you get n to be the dimension of F, K and H natural numbers with the K plus H at most n. And then one is given an H and F Coulter divisor with the dimension of the map associated to it, which is blah, blah, blah. Okay. Then you're given other what the hell? Sorry. Other H line bundle L K plus 1 dot L K plus H such that always Coulter divisor such that the dimension of phi Li of F is at most I, and then you get an F and big then bundle M, and then you have an inequality which is of this shape. You take M to the power what you have to take, which is N minus K minus H dot L K plus 1 dot L K plus H, and then you dot it with the H to the K, and that's at least the H0 of F lower part of H minus K. Okay, so maybe this as is written here is not very interesting, it's not very meaningful to you, but it also will not give you the proof, of course. But the upshot is that you get some intersection number, which is at least some number of section. So this inequality of this shape will exactly fit to study this intersection number. So you have this coefficient, you apply this, you get an H0, the H0 bound the rank here. So here you go back, and instead of this, you put a rank, and then you apply this and you get this. Questions, comments, disappointment? Hope is so indeed, a section of a paper, you have a section 2 with a lot of inequalities of this shape. Then section 3, the HN filtrations. And section 4, we put everything together. And we have to use that mu L is non-negative, and we get the slope inequalities. Okay. What time is it now?
It's 2:52.
You have 8 minutes.
Yes.
Do you want some fun or comments? Some fun of us? You have some fun side of the story if you like, just the results.
I do.
Do you like? Let's go some Fano. So we finish off with the results about Fano varieties. So Fano. So now we move to the Fano word, which is rather different. There is a, so we always have f from x delta to t, same notation, but here we are in the log Fano case. Okay. Now we have a first result, which is not with the Filippo and Luca, but it's with the so theorem with Zsolt, so myself, Zsolt, Patakfalvi, and now we get the spelling wrong, probably Maciek, Stanowicz. We have this result: if minus kx over t minus delta is an f, then f is locally isotrivial. Okay. So the upshot of this result is that you take E as before, up to a sign, so OX minus M kx over t plus delta. Now E is not an F in general. So mu L is negative. I mean, of course, if F is isotrivial, I assume F is not isotrivial. Okay, so maybe it is not isotrivial. So yeah, if F is not isotrivial, then this mu L will be negative, strictly negative. So all the above arguments do not work, because in the bound, when you bound and you do inequalities, you always have to have mu L positive. So in this case, the above topics will not go through the above argument. But we take F delta F to be the, always as usual the generic fiber, and we define delta to delta of f delta f, the stability threshold. Don't know if the spelling is correct. So we know that f, by the work of many people, of course, which I will not quote, but you know them very well, is k stable if and only if delta is strictly greater than 1. And of course, we know that on the Fano side, this k stability we have to look at. So we're gonna put ourselves in this setup. Remark that this is really k stability, it's not k polystability, because if you're k polystable, this is 1. I really want to put, I will comment on the polystable case, but I will want to put myself on the stable case. So the automorphism group is sorry, also the battery is going down. The automorphism group is trivial. Okay, so it's finite, sorry. So this delta is strictly bigger than 1. And now also let me define the Chow-Mumford-Lamb bundle here is minus the push forward of kx over t plus delta to the power n plus 1. So that's a Lamb bundle on t. So the theorem now I have with Jod-Patak-Falvey is this, that if you do minus kx over t minus delta, and then you sum, what you want to sum is delta times the degree of this lambda Cm divided by delta minus 1 times the volume times n plus 1, maybe doesn't really matter this, and then times a fiber. This guy is Neff. So this is not Neff. So on the fiber example, because you are in a Fano case, this means that we will have some horizontal curve along which this is strictly negative, because it's not Neff. So we'll have an horizontal curve, a multisection over which this is negative. What we are saying is this, look, if you add to this guy this time a fiber, then you will compensate the negativity. So the negativity of this guy along a section of f is at most that much. And these are numbers which are not very important. The one you have to look at is this, is delta minus 1, because we are in the k-stable situation, so delta is strictly bigger than 1. So this tells you really how much you are stable. Okay, so if delta is very close to 1, this number is very big. So you need a lot of a fiber to become Neff, because you will be very negative along a section. If delta is much bigger than 1, it means that here you don't have to add much, so you're not too much negative. In any case, this delta bounds you the negativity along a section of the map. Okay. And so now we test the theorem. So now we fix C a rational number. Is clear this Neff-Ness threshold thing? Question? Jesus, tell me. Question about
No,
this
I
thing?
said no question.
Okay. So take a number C now. A rational number, very bigger than 1, doesn't matter. And we introduce the Lamb bundle HC to be more or less that one. So minus kx over t minus delta plus c times, we have delta times the degree of lambda Cm divided by this delta minus 1, which is the really important quantity, and then I guess again the volume, and then n plus 1 of fiber f. And then the theorem I want to present you to conclude, which is joint to work again, myself, Luca Tassin, and Filippo Viviani, is that take, it was the following, take Q a natural number such that Q is bigger or equal than 1 divided by C minus 1, and Q of HC is Cartier. Then Q to the n plus 1 times HC to the n plus 1 will be at least the degree of f lower star of OX Q. So we get a slope inequality for this we get a slope inequality for this H line bundle. Of course, you can rewrite this for the anti-canonical. You will get something very complicated with the delta invariant and other things. But it's more elegant to write it down for this auxiliary line bundle. The things I want you to take away from this is that now the coefficient of the slope inequalities, which usually read of something of the geometry of a fiber, now they read the stability threshold. So the stability threshold becomes a very important geometric feature of the fiber, which plays a role in these slopes inequalities. Thank you for the attention.
Thank you very much for your very interesting talk, Giulio. Are there any questions? Yes, Giulio. You raised your, it's clapping.
No, it's clapping.
It's clapping. Sorry.
I actually have to go, so I can't ask a question.
Does someone else have a question, maybe? Okay, then let's thank Giulio again.
Okay, thank you very much. Goodbye, everyone.
Thank you very much. So then I will terminate the session now.